Section 3.2, we're going to discuss maximum and minimum values. Some of the things we are going to look in this section we've looked at before. We're just going to look at them more in depth today. And we're going to start by talking about this idea of relative or local extrema. So a point C, f of C, on an open interval where it's the maximum or the minimum value is a local or a relative extrema. And at that location, I mentioned this just a little bit ago when we were talking about your test, we either have a derivative of 0 or a derivative that does not exist. So there's two different sort of pictures that can happen. One is that it could look something like this. It's nice and smooth. This location we would say has a relative maximum. All right, it's a location where, at least in the general area, it's a peak of the graph. Now it may have that the graph goes on and does this afterwards. It doesn't change the fact that it's a relative extreme point. Relatively, in a close neighborhood, it's the biggest one. But it doesn't necessarily have to be the biggest one on the entire graph. Okay? So this one would be a location where the derivative is 0, right? If we drew the tangent line would look something like this, and it would have a slope of 0. So this is one picture that we could have drawn where we would have a derivative that is 0. I'm going to redraw the graph one time and draw it differently. Another option is it could have sort of maybe sharp turns. And it wouldn't even have to have two sharp turns. It could do something like that, and that would be okay. This piece right here, again, would be considered a relative extreme point. It is the sharpest point around, right? It's the highest, not sharpest, but the highest point around nearby, largest value. But at this point, the derivative actually does not exist. And the reason is because if I try to draw a tangent line on the left-hand side of this, it would be a tangent line with a slope that's positive, something like this, right? And the problem on the right-hand side is that the tangent line would have a slope that's negative. And they're not smoothing out to change. I mean, like it's either this one or it's this one, and I can't sort of touch in between. I can't sort of bend the tangent line to do that. And so we would say in this case that the tangent line does not exist. Okay? There is no tangent line at that particular point, so there's no derivative at that point. So this one is the does not exist case right here. I always like to talk about relative extrema and to tell a brief story of my family. I'm 5'4", and I might have shrunk a little because that's what happens as you start to age. I'll tell you that. So 5'4". If you were to talk with my mother, she would tell you that I am tall. Some of you are making funny faces at me. And she would tell you that I'm tall because in my family, I'm the tallest woman that's in my family. My mom's 5'2", my sister's 5'2", my granny was 5'0". I'm like 5 foot. I have a sister-in-law who's just under 5 foot. Everybody is shorter than me, so she thinks I'm tall. Well, she was in for quite a shock when she came up to visit us when we lived in Ohio, and we were youth pastors, and every youth from 6th grade until high school was taller than me. Girls, too, like all of them. I was the shortest one. It depends on the context that you're talking about as to whether you're tall or not, right? In my mom's opinion, I'm tall because the people that she's comparing me to are my family who are shorter than me. But in the context when we were talking about my youth group in Ohio, I was short. All right, fairly average, I think. But anyway, it depends on the context. And so on this graph in particular, as you're taking a look, this point right here in a local relative area, it's the largest point. But if you took all the points on the entire graph, it is not the biggest point, right? There's plenty of points over here, much larger y values. So you have to talk about in a local area. Now, these points where we have values that are either a derivative of 0 or the derivative doesn't exist have a special name. They're called critical numbers. So critical numbers are just possible places where we have maxes and mins. There are places where we have derivatives of 0 or derivatives that do not exist. Now, I keep saying that does not exist, and it does happen occasionally, but more often than not, the functions we're going to work with are going to have the derivatives of 0. Okay? Most of the time, we're going to be in this situation, not the other one. Okay, so they're not always the relative extrema, they're just potential relative extrema. And from your test, we looked at an exact example where it doesn't work, right? We looked at the graph of y equal x cubed. So if we were to take this derivative, set it equal to 0, we found out that this derivative is equal to 0 when x is equal to 0. And at that particular location, it's really not a max or a min, right? But it is a critical point. It's a potential point where there's a max or a min. It just isn't one. So it's one that we have to look at, check out, test, but it doesn't work. So what we're going to be doing is we're going to be taking equations and we're going to be finding these maxes and mins. So in order to do that, the first thing we're going to do is we're going to do what this statement here says, is that we're going to find all the places where we have the derivative 0 or the derivative doesn't exist. And then we're going to use those points as potential points that might work, and we're going to check them out. All right, so our first graph actually has an x cubed in it. It's not just x cubed, though, so it doesn't necessarily have the same features x cubed has in all respects. But take a look at the directions. It says to find the critical numbers by hand. Okay. Use your knowledge of the type of graph to determine whether the critical number represents a local max, local min, or neither. So the using the knowledge part, I'm going to show you how we go about using the things you already know to make that determination. All right, so what we are going to do, though, notice over here, both of these parts that are circled talk about the graph's derivative, right? So that's where we're going to start. We're going to start by taking the equation that we're given and find its derivative. So what is the derivative of x cubed minus 3x squared?
3x squared.
Mm-hmm.
6x.
Good. Does everybody agree with that? 3x squared minus 6x? You'll find that most of the derivatives we're going to be working with are a little bit cleaner, easier to maneuver and deal with than some of the more complicated ones from the last section. So that's going to be kind of a little bit of a reprieve for us. They're not quite as complicated for the most part. Now, obviously, this graph's a polynomial. It doesn't have any sharp turns. Okay, sharp turns happen when the graph has denominators having equal to 0, right? Or holes in the graph, things like that. Those kinds of things are not going to happen on a polynomial. Polynomials are nice and smooth. They don't have any does not exist values. Their derivatives work everywhere. So the only thing we have to check when we're dealing with polynomials is where it's equal to 0. Now, what I don't want you to do is I don't want you necessarily to throw things on each side and start simplifying. You have to be careful with the graph you're looking at. This graph has x squareds and x cubes, right? So what we're going to be looking at this graph is we're going to be looking at factoring. All right? So taking a look at what's already here, what is in common to both terms? An x and a 3. Now the 3 is not all that important, but we might as well pull it out because we can. But we definitely want to pull out the x. So if I take out 3x from 3x squared, what's left?
X minus 2.
The x first, and then from the negative 6x is the minus 2. Right. Is everybody good with that step? Okay. And then what we're going to do next is we're going to set each part equal to 0. So this is where your college algebra stuff that you've done before comes into play. So we're going to set each of these parts equal to 0. In the first place, we find out that x is equal to 0. And in the second one, we find out x is equal to 2. Now we're going to do something that you've seen me do once before. We did it, I think it was in 2.8. And we're going to do it again several times throughout this section, is we're going to draw a number line. And on our number line, we're going to plot the points that we just found. So 0 and 2. Okay? And we're going to test values in each of those intervals. Now you can pick any value in those intervals that you'd like, but obviously some values are easier to work with than others. For instance, what's a nice value between 0 and 2? 1. I would test 1, right? Now that's the most natural between there, but if you tested the number 1.5 or 3 over 72, it'll still work. It's just not going to be as easy to work with. Now what about the numbers before 0? What would you like to test over there? Negative 1 sounds good. And how about a number bigger than 2? 3. Again, you can pick anything in those intervals and it's going to work. So you've set up the number line with the critical values. These right here are our critical values, or critical numbers sometimes they're called. They're the ones that go onto our graph. And then we pick values between them. Now those values that we picked between them, we're going to test them, and we're going to test them into the derivative function. Does Sound good? What we're wanting to know is do we get a positive value or do we get a negative value? That's why it doesn't matter what number between the two values we pick, because we really only care is it positive or is it negative. And you're welcome to grab a calculator just to do it quickly to put it in there, because I'm not really caring what the value is, I just care what the sign is. So if I put in -1, 3 times -1 squared minus 6 times -1, do I get a positive or a negative? A positive. So I'm just going to write a plus for now. How about the value 1? What if you put in the number 1? What do you get? You do. You get a negative. And how about if you put the value 3 in? You get positive? That might be false. Did you check it? I didn't actually write that part of it down. So, did you get a positive? Yes? Okay, fabulous. All right, so we got positive, negative, positive. Now we did this before. Positive means the graph is doing what? Increasing. Negative means the graph is decreasing. Positive means the graph is increasing. So take a look at what you know. Well, if a graph is increasing and it's decreasing, what happens between those two locations? There's a maximum, right? Has to be. So this right here is a relative max. And what happens over here at 2 between decreasing and then increasing again? That's a relative minimum. So what we know is we know that we have a maximum at x equals 0, and we have a minimum at x equals 2. And depending on how your book is setting up the particular question, they may also want the ordered pair like the x, y coordinate. So if I wanted to know the actual location, like that is, if x is 0, what is y, how would I find that out? Yeah, I would plug it into the original. You got it. So this equation right here, if I plug in 0, what do I get? I get 0. So this maximum is actually at the ordered pair 0, 0. And if I plug in 2, what do I get? Do you have a question, Tristan?
Why are we plugging it into the original instead of the derivative?
Oh, because the derivative tells us where the graph is increasing or decreasing. The original tells us the location of the point on the graph.
Okay.
And we're just going to identify that the location of the actual place on my graph where I actually have this max or min is from the original graph. Yeah. What happens at 2? Is it -4? All right. That's what I have written down, so that's good. So this is 2, -4. And again, it just depends on how they ask the question specifically. In this particular wording right here, it just says, find the critical numbers by hand, determine if they represent a local max or min. So we wouldn't need the ordered pair in the specific wording of these directions, but some of the wordings of the directions do want the ordered pair. They'll say something like, find the critical point. A point is an ordered pair. A critical number is just an x value. Yes?
So if it's worded like this, all we would need to put is the maximum at x equals 0. And
Yes. You're right. Yeah. Okay, any questions on that one? Okay. Let's take another example. Again, this one says find the critical numbers by hand. That's the same directions we had before. It says, if available, use a graphing technology to determine whether the critical number represents a local maximum or neither. When they're telling you this kind of description, what they're saying is you don't necessarily have to draw that sign chart. I'm going to draw it so you can see what it would look like if you were dealing with it where it didn't give you sort of the permission to check your calculator. But we'll check the calculator at the end to verify that it really is what our sign chart's telling us as well. Okay? So at the starting of this, it says to find all critical numbers by hand. So what does that mean, to find critical numbers by hand? Yeah, take the derivative, set it equal to 0. So we're not looking on a graph to see where it has these peaks and valleys. We're actually going to do the derivative by hand. So this one has a fun derivative because it is a quotient rule. It's not a horrid quotient rule though, okay? So, right, I mean, it could be much worse. All right, so what does the quotient rule tell me I'm supposed to do? Okay, Okay, denominator times the derivative of the numerator. So what's my derivative of my numerator? 2x, great. And then what? Uh-huh. Great, and the derivative of the denominator is just 1. And then all of this is over the denominator squared, and some of you like to leave that part off when you do quotient rules. So be careful to remember that piece of it. Okay, so that's the version that you left it in when you were working on your basic skills quizzes, right? All right, so we're going to clean up the numerator now. If I clean that up, I have, let's see, 2x squared plus 4x minus x squared plus 2. Did I get all the pieces in there okay? And all of this is over x plus 2 quantity squared. How does that numerator simplify? X squared plus 4x plus 2 over x plus 2 quantity squared. All right, there are two possible things that could happen. We could have the numerator equal to 0, and that would give me a place where the derivative is equal to 0. Or we could have the denominator equal to 0. If the denominator equal to 0, what would happen? We get either a whole or an asymptote, right? So there'd be a possibility of one of those two things happening. So the denominator equal to 0 is a location where the derivative would not exist. So we are going to test both of those features. So if we take the numerator equal to 0, what's going to happen? Like, how would I find the numerator set equal to 0? We could try to factor. Why do you think I said try? This one doesn't factor, unfortunately, because of that 2. I can't multiply 2 by anything and add things together to get 4. It won't work. So if I'm stuck and I can't factor something, what's our next options? Quadratic equation or completing the square. That is an option. People don't usually go with that one, but it is an option. All right, so quadratic formula. Do you guys remember that? Yeah? Okay, hang on a second. Let me get myself some more space. All right, quadratic formula says what? X equals negative 4 squared minus, yeah, well, times 1 times 2, right? All over 2 times 1. Very good. So I have negative 4 on the outside. What is the part underneath the radical? It's called the radicand. What does that simplify to? It is. It's 8 first. We'll put an 8 down first, and then it's all over 2. All right, so I am quite sure in trig that you guys learned to simplify square root of 8. You probably learned before then, but I know it happens frequently that you have to deal with radicals in trig. So this one actually ends up being 2 square roots of 2, right? Because 8 is 2 times 2 times 2. And it's all over the number 2. And at this point, we're allowed to reduce because all 3 of these divide by 2. So both pieces of the numerator are divisible by 2. So when we divide this, we end up getting negative 2 plus or minus square root of 2. These are x values all the way along. We also have a potential place right over here that's a critical number where x is equal to what? What would I have to do to let the denominator be 0? Not 2, but negative 2, right? So we actually have 3 critical points. So what I'd like for you to do is I'd like you to grab your calculator, because it said we were supposed to use technology on this one. So grab your calculator if you have it with you. If you don't, watch your neighbor. Most of you probably have it with you. Okay. What you're going to do is you're going to enter the original equation into y equals. Okay. And if you aren't sure what sort of evaluation points you should be looking at. You can approximate this piece right here by just taking your calculator and putting in -2 plus the square root of 2, -2 minus the square root of 2, and seeing roughly what those, like a decimal approximation are for those, so you can make sure your window's big enough. -10 to 10 is perfectly big enough on this one, but if they were values you weren't sure were in your window, you could check that way. All right, so my graph looks something like this. Does yours look something like that? It might have tried to attach these two pieces together, but in reality, of course, there is an asymptote there. Some of your calculators, if they're as old as this one I'm working with, may have attached it. Some of them have improved and they won't try to attach those together anymore. What is that dotted line doing? We call it a asymptote. Where is it occurring? Yeah, this is occurring at x equal -2. Whoops, left my negative out there. At x equal to -2. So I don't have a maximum in there. There's actually an asymptote there on this particular graph, right? Over here, though, what is that point? Yeah, it's -2 minus square root of 2. Is it a max or a min? It's a max, right? And what about the point right over here? -2 plus the square root of 2, and it's a min. And it's very strange because if you take a look at it, my maximum value is smaller than my minimum value. And that feels a little bit weird, right? Yeah, it definitely feels weird, but remember it's a local issue. Locally, it's the biggest value. Locally, it's the smallest value. Let me show you in terms of a number line what happens if you were to try to do this one, and they didn't want you or intend for you to use a graph to justify your answer. So what we did already on this problem is exactly what they intended. I just want you to see what happens if you actually have to justify it with a sign chart, okay? So we have one value that's -2 minus square root 2. Can somebody give me a decimal approximation for that? Just a couple of decimal places for -2 minus the square root of 2.
Say -2 minus square root of 2.
Uh-huh.
-3.414.
Okay, so -3.41 will be great. And then we had the x value of -2. And then we had an x value of -2 plus the square root of 2. Can you find that one for me too, Tristan? It's still negative, but...
-0.5858.
All right, so I'll just put -0.58, it's fine. The reason I ask for those is because if I'm going to test a point, I need to know roughly what points I'm looking at to try and test between. Right, so I need to pick a value that's smaller than -3.41, so something like what? Is -4 okay? Will that work? How about a value between -3.41 and -2? -3 would work. How about a value between -2 and -0.58? -1. And then a value bigger than -0.58. 0 is my favorite. If I can use it at ever, I will use it. And we test these points into which function, the original or the derivative? The derivative, because the derivative tells us if the graph is going up or down. You guys remember that? Do you remember that? Once I said it, did you remember that? Okay, good. All right, so remember the derivative tells us if the graph is going up or down. So we're going to take these four values. You've already got them in your calculator, but you've got the actual function in your calculator. So let me remind you of how to use your calculator to find a derivative. I think I showed you guys this once before. Okay, so your function's already in the calculator in y1, right? All right, so go back out to your regular screen in your calculator. We're just testing the point in the derivative anyway. You're going to hit Math 8, which either says inderiv or it has what looks like a dy dx kind of a notation, right? All right, so in deriv, we want the function y1. So you hit vars, y vars function y1. So that's the function you're taking the derivative of is y1. If you have the old-fashioned notation like I do, you put comma x and then comma the value you're looking at. So I'm going to do -4. If you have the dy dx, you need to make sure it's got a dx on the bottom, because right now it just says it has a blank spot. You put your y1 after it, and then it has like a valuation bar, I think, doesn't it? Have a line? And it says down here x equals or something like that. Who has those calculators? The ones that are like that. Is that what yours says, Jennifer? Okay. And then down here you put the x equal 4. So your notation looks like one of the following. Let me write the two notations on here to remind you. It either says in deriv, and you've put in y1, comma x, comma, and then in this case I put in -4. Or it starts out with dy, or maybe it doesn't even have a y, I don't know. But you're going to put x down here at the bottom. You're going to put a y1, and then there's a line, and it's going to say x equals -4. Does it match one of those two?
How do you put y1 on
You hit vars, which is right underneath the arrow pad. You go over to y vars, vars for variables, and then you hit function and y1. All right, so plugging in x equals -4, do you get a positive value or a negative value? You get a positive value. I'm going to just tell you what happens in the next pieces so we can finish this one up before we leave. The next one is going to give you a negative value, and then you get another negative value, and then you get a positive value if you insert those. And if you don't like my fancy in deriv business, you could just take the equation you found the derivative for and just put the numbers in by hand too. That works just fine. All right, so notice what happens here then. This graph is increasing, decreasing, decreasing, increasing, right? Well, when it goes from increasing to decreasing, right here we have a maximum. And over here, where it goes from decreasing to increasing, we have a minimum. And look here in the middle, what happened? Decreasing, decreasing, right? Now, we know that's happening because we have an asymptote, but even if we didn't have an asymptote, decreasing, decreasing would simply mean we don't have a max or a min. It doesn't follow one of those two sort of formulas or patterns.